Hello everybody, my name is Daniel Silasko and today I want to talk about discrete virtual rotations in virtual reality. When we are talking about virtual rotations, what we usually are referring to are rotations of the camera viewpoint around the yaw axis. Physical rotations in virtual reality, that is visualized here, synchronize the viewpoint completely to the head orientation in reality. In virtual rotations, however, rotation is artificial. As you can see here, our head is not turning in reality, but our view rotates in virtual reality. Rotations in VR can also follow a mixed model. An example are rotation gains, where the virtual camera, for instance, rotates faster than our physical body. Relying on physical rotations should be the goal of every virtual reality application, because their virtual counterparts come with a number of disadvantages. The maybe biggest is that the induced mismatch between the visual and the vestibular system are potentially raising cybersickness. Also, the user's spatial awareness can be negatively influenced and it's less natural. All this can be observed for virtual translations as well. So, why are we talking about virtual rotations here at all? There are many scenarios in which physical rotation is limited or not possible at all. Some of them are depicted here. Okay, then we have to tackle the challenges that virtual rotation comes along with. A solution at least to cybersickness can be teleportation. The method is widely adapted, and its discretization of motion can also be applied to rotations. As we can see here, the viewpoint orientation is jumping. Discrete virtual rotations are already researched, for instance in the work of Sargunam and Ragan. In these methods, the users specify a direction, left-right, and then their viewpoint is rotated in this direction instantaneously. Farmani and Tether implemented rotational snapping, a hybrid method, where the rotation was continuous and only by exceeding a specific threshold of turning speed, discrete rotations were applied. When searching for a translational sibling, there is for instance dashing, where the users specify a direction with their viewpoint orientation and then move into this direction very quickly. However, the majority of teleportation methods use target selection, not directional input, and thus the question arises if there's also a pendant in virtual rotation, something like a rotation selection method. There's actually work that investigates orientation selection together with the target selection process of target-based teleportation. But we did not find any work that deals with egocentric orientation selection. This observation led us to the point where we wanted to have a more structured view on different virtual rotation techniques. So far, we named directional methods, one of which was rotational snapping, and we asked if there are also egocentric techniques that let the users directly select their target orientation. We decided that both paradigms differ in their way of target acquisition. Initially, we have restricted ourselves to discrete methods. For a moment, we want to widen that up again. This differentiation of methods that we implicitly made here already, we call continuity. And something important to note is that there are not only the binary classes continuous and discrete as shown here for the simplicity of visualization. A classic directional and continuous rotation method is applied by a joystick interface. We know it from gaming and VR experiences that made us sick. Then there are also embodied versions of this method, which are called scrolling by Langbehn et al. We want to differ between these methods and thus included another dimension, body-based, which is also a scale. Last, we think that we can also include rotation gains in our classification when considering the human body as pointer that we are selecting rotations with. At the end, there are some gaps. And they might there be for a reason. Maybe it's because we did not find your work, so tell us, or it's just a dumb idea to do so. Restricted to discrete methods, we wanted to find out with this work. To do so, we implemented 2 by 2 equals 5 representatives. 2 discrete and directional methods, both executed rotational jumps of 11.25 degrees every 0.4 seconds at maximum. In the controller-based method, the directional input came from a joystick, and in the body-based interface from a left-right movement of the upper body. All interfaces were used seated. For the rotation selection, we initially implemented 3 methods. two controller-based versions, one using the handheld controller as a pointing device, the other using the joystick to define a direction. The latter worked comparable but was not preferred by the users, so we will leave it out in the following. With the body-based technique, the target orientation was selected with the upper body leaning into the desired direction. We conducted a remote user study, allowing Oculus Quest 1 and 2 as target devices. We reached 10 female and 10 male participants with an average age of 25.5 years. Only 6 of them had prior experiences with virtual reality. In the experiment, the participants had to perform a primed and a naive rotational search task. Both tasks were conducted in a semi-random generated virtual environment like the ones depicted below. For the primed search task, we used and slightly adapted a design created by Langbehn et al. Here, the participants repeatedly had to find a target cube behind them, and at the start, an arrow showed them the direction they have to search in. When having accomplished that, participants were asked in which direction they started in. We added a rapid pointing task here to reveal potential effects of lower cognitive spatial orientation. The naive search task was inspired by a design of Freitag et al. Here the participants had to find specific objects in the same scene. Let's directly jump into the results and have our first look at the factor of body-based interaction. As expected, the body-based methods were slower in task performance than the device-based methods. But we further also not found a significant advantage in spatial orientation. Maybe most remarkably, the SUS scores of the body-based methods were lower as well, especially for the body-based selection method. We already mentioned that the degree of embodiment is not binary and likely multidimensional. Thus our findings can only be a first indication and not cover the whole design space. Moving on to the factor target acquisition. We do see the absolute pointing error of a first rapid pointing on the left and of a second corrected pointing on the right. And as expected, the selection-based methods provoked a significantly higher absolute pointing and configuration error in the rapid pointing. However, this effect vanished in the second pointing, where people had time to correct their input along landmarks and so on. Last and maybe most interesting, the task performance looked the following. On the left, there are the results for the primed search task, and on the right, for the naive search task. As expected, the selection-based pointing methods were faster in the primed search task. Surprisingly, the exact same pattern is mirrored to the naive search task as well. After having seen all the results, we also performed some tests on potential interaction effects in some of the measures, but found no evidence in any. One observation that we made that can explain the results is one remarkable positive trait of selection-based techniques is they can be used as directional techniques with variable jumping distance, which also means there is also no parameterization. And participants in part did exactly this. We have to add that in this study we had an isolated view on virtual rotation, while in reality most of the time rotations come together with travel and it's questionable in how far results transfer. We talked about parameterization. Especially the directional methods rely on parameters, and while most of them were tested empirical before or were based on related work, this is still a factor. Last, cybersickness was not investigated in this study, while it was the main motivation for it. We assumed none of the methods is adding to sickness, which has to be proven. For future work, we found that selection-based virtual rotation works well, and we want to have a deeper look into this. We already started to investigate the method being included in a regular travel interface. That's it for now. Thank you for your attention.